Hello everyone. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering, Edra, Ichalkaji, which is at Kolhapur district, Maharashtra. Today we are going to see the introduction to finite element analysis or finite element method, or the principles of finite element analysis. We're going to see the principle of finite element analysis, that is the finite element method or finite element analysis is computational technique used to obtain approximate solution of boundary values problem in engineering. The boundary value problems are also called field problems. The field is the domain of interest and most often represents a physical structures. The field variable are the dependent variable of interest governed by a differential equation. The boundary conditions are the specified values of a field variable, or we can say a related variable such as derivatives on the boundary of the field. If you see, for simplicity we can say, at this point we assume a two-dimensional case with a single field variable, that phi x and y, to be determined at every point, that is p of xy. If you see, this is p of xy, this is boundary, and such that a known governing equation or equation is satisfied exactly at the every such points. Here in figure this, if you say this a figure, that general two-dimensional domains of a field variable phi x and y, and a B is a three node 1 2 3 node finite element defined in the domain, and this third is the additional element showing an partial finite element mesh of a this domain. A finite element is not a differential element of size dx and dy into dy. That node is a specific point in the finite element at which the value of the field variable is to be explicitly calculated. So that we need shape function, that shape function, the value of the field variable computed at nodes are used to be approximate the value at non-nodal points, that is the element interior, by interpolation of the nodal values. For the three node triangle example, the field variable is described by the approximate relation, that is phi x and y, that is equal to n1 x and y phi 1 plus n2 x y phi 2 plus n3 x and y phi 3. Here n1 n2 n3 as nodes. See nodes, if you see phi 1 phi 2 phi 3 are the values of field variable at the nodes, and the n1 n2 are the interpolation functions. These are the interpolation functions at nodes, and also known as shape function or blending functions as well. In this finite element approach, the nodal values of field variable are treated as unknown constants. These field variables are unknown constant. This field variable is considered as unknown constants that are to be determined. The interpolation functions are most often polynomial forms of the independent variables and derived to satisfy certain required conditions at the nodes. If you see, the interpolation functions are predetermined, that known functions of the independent variables, and these functions describes the variation of the field variable within the finite element. If you see a degree of freedom, this is a very important point. uh, uh, Again, a two-dimensional case with a single field variable, that is phi x and y. The triangle element describes is said to have 3 degree of freedom: x, y and z. As three nodal values of field variables are required to describe the field variable everywhere in the element, that is in scalar. If you say phi x of y, that is equal to n1 x y phi 1 plus n2 x y phi 2 plus n3 x y phi 3. In general, the number of degree of freedom associated with a finite element is equal to the product of the number of the nodes and the number of values of the field variable, and it's possibly its derivatives as well, and that must be computed at at each node. If you see a general procedure for finite element analysis, the pre-processing is first point, that in that defining the geometric domain of the problem, and then define the element types to be used, and define the material properties of the elements, and next define the geometric properties of the elements, that is length, area and the what kind of that is, and define the element connectivities, a mesh, the model, and define the physical constraints, that is boundary conditions, define the loadings. If you go to solution, the computer computes the unknown values of the primary field variables, and then computes values are then used by backup substitution to compute additional derived variables such as reaction force and elemental stresses and heat flow. If you see, in the fast processing software contains sophisticated routine used for sorting, printing and plotting selected results from the finite element solutions. Stiffness matrix, if you see a stiffness matrix, the primary characteristics of a finite elements are the embedded in the element stiffness matrix. For a structural finite element, the stiffness matrix contains the geometric and material behavior information that indicates the resistance of the element to deformation when subjected to loading. Such deformation may include axial bending, shear, and the torsional effects. For finite elements used in a non-structural analysis, such as fluid flow and heat transfer, the term stiffness matrix is also used, since the matrix represents the resistance of the element to change when subjected to external influences only. If you see the linear springs as a finite element, this is a linear spring attached u1 and u2 displacements. A linear elastic spring is a mechanical device capable to supporting axial loading only, and an elongation or contraction of the spring is directly proportional to the load applied axial load. The constant of proportionality between deformation and load is referred to as a spring constant or spring rate or spring stiffness K, right? And has unit of force per unit length. As an elastic spring supports axial loading only, we select an elemental coordinate system that is known as local coordinate system as an x-axis oriented. So here in this figure, the linear spring element with nodes, these are the two nodes, and nodal displacement and nodal force. There is nodal displacement and these are the F1 F2 nodal force, and this is x direction force, and this is a load deflection curve. This is load deflection curve, force versus deflection, that is u2 minus u1, that is F. So now if you see here, assuming that both the nodal displacements are 0 when the spring is undeformed, isn't it? Undeformed. This is 0 when this is undeformed. The net spring deformation is given by delta equal to u2 minus u1. Thus u2 minus u1, change in displacement, isn't it? So u2 minus u1. So here we can say that, and the resultant axial force in the spring is F, that is equal to K into delta. K is spring stiffness, K into change in the displacement delta, and delta is nothing but u2 minus u1. For equilibrium, F1 plus F2 equal to 0, isn't it? Equilibrium, F1 equal to F2 equal to 0. If this is and this is also equal to, then you can say this would be 0. Then I can write this F1 equal to minus F2. Then the term of the applied nodal force as F1 equal to minus K of minus K. This is, and F1 that is equal to minus K of u2 minus u1. So F2 is what? Minus minus, again this would be K into bracket u2 minus u1, which can be expressed in the matrix forms K minus K and minus K and K, or you can say this K of minus K, or minus K and plus K, and this is K minus K. So displacement of u1 and u2, and forces that is equal to force F1 and F2. Clear? Or you can say a matrix of Ke and U that is equal to F, where Ke is nothing but this matrix, that is K minus K and minus K, and K that is stiffness matrix for the one spring element, that is defined as the element stiffness matrix in the element coordinate system or local system, that is U is the column matrix, or this is vector of the nodal displacement, and F is the column matrix or vector and of the force of the element, nodal element. If you see this equation, F1 F2 that is equal to Ke U1 and U2 with Ke K minus K and minus K of K. Here F known, that is equal to K into this X is unknown, this displacement is unknown, and the equation shows that the element stiffness matrix for the linear spring element is 2 into 2 matrix, 2 into 2 matrix. This corresponds to the fact that the element exhibits two nodal displacements or degree of freedom, and that the two displacements are not independent, that is they are not independent, that is the body is continuous and elastic. Here the fourth more, the matrix is symmetric, 2 into 2, that is matrix is symmetric. This is the consequence of the symmetry of the forces, that we can say equal and opposite to ensure the equilibrium. Also the matrix is singular and therefore not invariable. That is because the problem as defined in the incomplete and does not have a solution. The boundary conditions are in that condition, the boundary conditions are required. This was for a, a single spring. You can same you can do multi springs also. You can get the equations as well. So here this we have gone through a little principle of FEA of matrix of a we have gone through shape functions, even boundary conditions, a degree of freedoms, stiffness matrix, and this linear spring as a finite element. So next video we'll see another part of the FEA. Thank you.